Man, you're extra. It's just a line in my book. So if you can email it back to me right out to someone, when the owner, because I don't have the same, mine doesn't align, so I don't think I'm looking at the same thing. Yeah. Okay, let's see. So I told the juniors this morning, I'll tell y'all too. Guys in the back. I spent days trying to work out this thing for the dance, and I tried to see if I could get enough people to respond to commit that I knew it would be worthwhile, because the only date I could now secure was May 30. And I only got 10 or 9 people that responded, but I need at least 20 for it to be worth it financially, because I do have to rent the place and everything. And so I'm gonna call it for this spring, but I'm gonna move it to the fall. And anybody who is still here and wants to come in the fall, you can still come in the fall. I'm terribly sorry, I tried to do it, I really did. They changed the whole process and now it's automated and it's dumb. You used to email a guy and say, which of these dates is available? And he would tell you and you'd say, thank you. Now it's an app and you have to reserve a time slot for the day. But in the past, it was always just the full day. So I went in to reserve the time slot for the day, and my second toggle, I missed the PM and I had it at an AM, which didn't make sense. But then they came back and they're like, which one did you want? And I'm like, well, obviously the full day, isn't it for the full day? And they're like, yeah, it is, but somebody else already rented it because the rest of the day was available because of how I toggled, which is stupid because it should be the full day. So I pointed that out to them, but there's nothing I can do to change it now. And the only other date available was May 30, and only 9 people came back and said they could go. So I can't do a dance for 9 people. That's crazy. So we'll look at doing one in the fall and in the spring. All right, so dudes in the back, we are not going to chitter chatter today, right? We're not going to like, blah, 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 blah. I'm going to go ahead and start a little bit early. Here's why. I really try not to do death by video. I try to throw in little short videos. I try not to make them too long. This lab had a lot of videos, but today at the end of the lesson today, I have a video that is considerably longer than anything I typically show, but it's very cool. And so I wanted to share it with y'all because also this lesson is fairly short and I wanted something to add on to it that I thought would be valuable, and it's going to lead us into our next bit. So I'm going to go ahead and start because that way we won't run out of time. Cool? Are we good? Everybody's ready? Yeah. Oh, you're saluting me? All right. Yes. Can you what? Can you travel there? There are all kinds of rules about it. I'm not even sure what those are. But okay, y'all in the back said you weren't going to chatter, but you already are. All right, let's do it. So we're talking about nuclear chemistry today. This is our one and only day that we talk about it. And then we move into organic chemistry. So it's not like it's a really, we're just going to whip through it. All right. So let's talk about atomic nuclei and nuclear stability. What is going on with nuclear chemistry in general? Do you remember back at the beginning, we talked about strong nuclear force. You have protons in a nucleus, and those protons want to repel each other, right? It's just like taking 2 positive poles of magnets and trying to push them together. You have problems, right? You can't make it go. They are repelling each other. So the nucleus of an atom occupies a tiny fraction of the volume. What's in the nucleus? PJ?
Protons and neutrons.
Protons and neutrons are in the nucleus. All right, and they would normally repel each other. The protons would normally repel each other, but because and that would cause it to fly apart, but because of the strong nuclear force between the nucleons, at least all stable nuclei except for hydrogen contain at least one what? Neutron, right? So it's the strong force of the nucleons that keep the atom from flying apart because the protons would otherwise repel each other. Everybody gets that? That makes sense? Yep. Yep. Dudes. All right, so the mass defect. All right, now there's a difference between the mass of an atom and the sum of the masses of its protons, neutrons, and electrons. So if you take, let's say that these separate images here, your purple are your electrons, let's just say your green are your neutrons, and your light blue are your protons. If you add up the individual masses of all of the individual particles, you get this number. But when you put them together as an atom, you get that number. Where does the energy go? Where does the mass go? Sorry, I just gave the answer away. Yes, sorry. The mass gets converted to energy, and it's called the mass defect. So mass getting converted to energy is kind of a newer concept for us. We've talked about how you have conservation of mass. It's neither created or destroyed, that it can change phase, but it can also change to energy. And energy is also neither created nor destroyed. We talked about different kinds of energy in physical science, right? You got, potential energy, everything from elastic potential to gravitational to chemical to, then you have kinetic energy and, That's where we're going. Yep,
You're going to say that mass is like a form of energy, and then energy is still not created or destroyed.
Well, that's where we're getting here. So we're going to come back to it in just a second. But that energy that gets converted into what gets lost as mass, that mass that gets converted into energy is called nuclear binding energy. So Asher just said it. This is where our buddy Einstein comes in. All right. So you have nuclear reactions, like chemical reactions, are accompanied by changes in what? What do you have? What changes? Changes in, what are we talking about? Energy. Yeah. Changes in energy. All right. And the energy changes in nuclear reactions, however, are enormous compared to those in chemical reactions. There are small changes in energy, but in nuclear reactions, there are massive changes in energy. So, in fact, energy changes in a typical nuclear reaction are so large that they result in a measurable change in mass. In this section of this lesson, we describe the relationship between mass and energy in nuclear reactions and show how seemingly small changes in mass that accompany nuclear reactions result in the release of enormous amounts of energy. So the dude who explained this best is our buddy Einstein, and it's with this equation that Asher elucidated a second ago, E equals mc squared. What does C stand for? Speed of light. What does E?
Energy.
Energy and mass. Okay, so we have energy and mass. So energy is going to be expressed in joules, and mass is going to be expressed in kilograms. So when we put it, Lucy, did you want your coins? Yeah. I'm gonna put them, sorry, put them right here for her. So this whole, right there. So this whole relationship has been expressed by Einstein, and this is the equation because he's super smart. Now, this is one of those equations that not even, non-sciencey people even know it, just because it's sort of in our vernacular, right? It's kind of funny. My doctor's name is Alan Einstein, and he's distantly related, right? But he plays on that, like he used to call his practice EMC2 care. Now he calls it Einstein Genius Care. But his wallpaper behind his front desk is all Einstein's equations in his handwriting. And he has pictures of Einstein all over the place. And I was at a museum once where they had a little Einstein, and he was like in little boxer shorts and a little undershirt, and he was standing like this, and you just dressed him in different magnet. Well, he's like a magnet. You put him on the fridge and you changed his clothes. Like a paper doll and a magnet. So I brought that to him. So now that's up, he likes it. Good thing to be able to play on. Cool name to have. So let's talk about nuclear change. All right. So nuclear change, we have this thing called the band of stability, and they're going to show it to you here, and then we're going to talk about it a little more. But if an atom is stable if the forces among the particles that make up the nucleus are balanced. An atom is unstable, and what's the other word for an unstable atom? What do we call it? It's unbalanced, but what do you call an unstable atom? what do you call it? Hey, it is radioactive if the forces are unbalanced. So if the nucleus has an excess of internal energy, you've got a radioactive atom. And an inability of the atom's nucleus, inability of an atom's nucleus may result, instability, I can't read, sorry, my contacts are crazy right now, may result from an excess of either neutrons or protons. All right, quick video. These are quick ones because we have the long one at the end.
From the Jack Welch Medical Institute, State University.
So I'm tired.
You don't want those food like Puerto Rico, whether it's a chef takes
I'll
the
go.
menu or a local favorite spot with no sign.
How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video.
Thanks.
A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of two neutrons and two protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta minus decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta minus, or beta plus decay.
So what I want you to notice, go back 2 seconds, right there. Notice it says neutron changes into a proton and loses an electron. Neutral particle splits into a positive and a negative, right? And then here it says a proton changes into a neutron and loses a positron or a positive particle. So you're actually having changes in your subatomic particles. Something that's important to keep in mind. What determines what element you're dealing with? Which of these subatomic particles determines the element you're dealing with, Asher? Protons, right. Because what is it if you have a different number of electrons? You have an ion. What if you have a different number of neutrons? You have a isotope, right. So what you have here are a different number of protons, and that changes the element. Now your atom is a different element, and that's what's different about radioactive decay as opposed to just becoming an isotope or an ion.
Beta.
So this is that band again that he was talking about in the video. This is your little band of stability, and this is known quantity. This is like a standard. We talk about things that we know, numbers we know, values that we know in science that we can plug in. That's what this is. These are known quantities. So a belt of stability makes it easy to determine where the alpha decay, beta decay, and positron emission or electron capture occurs. So your alpha decay is located where? Do you see it on here? Anybody see alpha decay? James, do you see it? Right here? Yeah. See that's your symbol, your alpha decay. So it's at the top of the plotted line because the alpha decay decreases the mass number of the element to keep the isotope stable. And it's accomplished by emitting an alpha particle. What's an alpha particle? It's just, right, which means it's basically helium. Okay. So in this decay pathway, the unstable isotope's proton number, which we call pp, is decreased by 2, and its neutron number, Nn, is decreased by 2, which means the nucleon number, Aa, decreases by 4. So in your beta decay, you've accepted a proton, so it changes the amount of protons and neutrons. The number of protons increased by 1, and the neutron number is going to do what, do you suppose? Xander? Yep. So it's going to decrease by 1. And this occurs in unstable nuclides that have too many neutrons and lie above the band of stability. So this is your beta up here, above your band of stability. And then your beta plus decay is down here. And this is when you lose an electron and the, emission and electron capture when the isotope gains more neutrons. So positron emission, remember the positron is like an electron, but it's positive instead of negatively charged, right? Positron emission and electron capture are below the band down here, see it? Because the ratio of the isotope has more what than neutrons? Okay. All right, so it has more protons than neutrons. All right. So this is a standard. We know this information, so we can plug it in. We don't need to do this every time, right? It's right there. So as with all pathways, the daughter nuclides are not on the belt. The subsequent decay pathways will occur until the daughter nuclei are on the belt, and that's when they are stable. So let's talk for a minute about fission, nuclear fission. So in nuclear physics, and let me just say this, make this one really clear, and we'll say it one time. I will disown you if you mispronounce this word. It is nuclear because it is dealing with the nucleus, right? It is not what? It is not nuclear. It is never nuclear. It's not nuclear medicine. It's not nuclear weapons. It's not nuclear power. It's nuclear. Nuclear because it deals with the nucleus.
You could find a different name to assign nuclear to it, like people actually say different words instead of this mispronunciation.
Say what?
So we should assign a meaning to the word nuclear.
Oh.
It actually means something else.
It means scientifically uneducated. That's what it means. So don't do it. Don't do it, right? We had a president that did it, and every time he did it, I wanted to jump through the TV screen and strangle his handlers for not correcting it 100 times. It was George W. Bush. He could not say the word to save his life. So I mean, come on, somebody teach So in nuclear physics and nuclear chemistry, nuclear fission is a reaction or radioactive decay process in which the nucleus of one atom does what? What happens in fission? Jordan.
The nucleus split.
Nucleus splits, right? He did it. Yes, your nucleus splits into two smaller nuclei. We're good. All right. Nucleus splits. Yes, you're correct. You're correct.
I said it.
He's all right. You're good. You're good. All right. So in fission, you have split a nucleus. Guys, back on topic. All right. So fission is when you have split the nucleus. Now you're talking about an itty bitty, tiny atom. But splitting the nucleus of an atom releases an enormous amount of energy, right? So what happens if you split the nucleus of an atom? What do you get? Caitlin, what do you get? Ah, yes. Show everyone with your hands what you were doing. Yes, like the atomic bomb, for example, right? So nuclear fission is the subdivision typically of a heavy atomic nucleus. The heavy ones are less stable. You remember when we had our periodic table up that all of the radioactive elements were way down at the bottom, right? They're the heavy ones. So typically we use uranium and plutonium because they're very heavy, and it splits them into two fragments of roughly equal mass. The process is accompanied by a large release of what? Energy, huge amount of energy, huge. So fission occurs when a neutron slams into a larger atom, forcing it to excite and split into two smaller atoms, also known as fission products. That's what we call them. Additional neutrons are released that can initiate what? Then what happens? A chain reaction. So yeah, this is what happens when you have a nuclear bomb or anything else where you're splitting, where you have nuclear fission. You have one atom explode, one atom splits, and it causes a chain reaction where all of the atoms around it then begin to do the same thing. And that's why it's so huge. And that's also why it can be so uncontrollable. When an atom splits, a tremendous amount of energy is released. And like I said before, it's typically uranium and plutonium that we use for fission and in nuclear power reactors because they're easy to initiate and control.
What do we use not from?
I'm not sure what else would be in there. There's in a minute, I'm going to put up a whole list of all these different things that we use, and there are probably some for maybe smaller reactor type things, but these are what we use in general. So the energy released by fission in these reactors, in a nuclear reactor where you're trying to make nuclear power, it heats water into steam, which turns a turbine, which you then have that rotating turbine, and that is used as a generator for electricity. So that's how we're getting our nuclear power. It's heating water. The other ways to heat water are burning fossil fuels, burning wood, things like that. But that releases soot, emissions, pollution. Nuclear power doesn't release pollution into the air, but you do have waste products that you have to deal with afterwards. And there are ways to deal with them that are very safe when done properly. And this is what we mean by chain reaction. You get your little fissionable nucleus, as they call it. It splits. That causes it to smack into these guys, and that smacks into those guys, and you just get, it's just like a domino effect, right? Sorry. So if you look, here's fission versus fusion. So in both of these, we have fission on the left, fusion on the right. So fission you're splitting your larger atom into two smaller atoms. But fusion is when you take a small atom and you're going to combine two small atoms to create a larger one. Typically, what we are using for that is hydrogen. You heard of hydrogen fuel cells? That's what we're doing. So in that case, what we're trying to do is fusion. Now, we're really good at fission and energy production. We've kind of mastered this. I'm going to say that with a little knock on wood, just in case somebody blows something up soon. But you know what I mean? We have lots of nuclear power plants. Anybody ever driven past one? I've driven past 2 or 3. You can usually see them because they have those big towers like the opening of The Simpsons and the opening credits, right? That shape, there's lots of steam coming up. You can usually see it. We're good at this. We've been doing this for a long time. We've gotten successful at it. We're still working on some of this fusion business, but here's why we should be working on it. Fission is 1 million times greater than other energy sources. The amount of power it produces is 1 million times greater than other sources. That's pretty cool. And you're not releasing all the soot and yuck into the air. Fusion is 3 to 4 times greater than fission. So if we can master this, we can power a lot from one source, right? So that would be, this is a goal. We're looking towards this. Will be cool if we can actually master it. So the sun is the best example of where fusion is used to produce energy. Oh, I know.
You see, we test, and then we. If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take 2 hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get 2 atoms to fuse. 2 protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse. And that's very, very rare.
To force protons together takes immense amounts of heat and pressure generated by the invisible hand of gravity.
Yes, micro.
The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
With gravity crushing things down, things get close enough together and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, they bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
So yeah, you've got fusion going on around you all the time, but it's just not something we've been able to replicate on a grand scale yet. So this is what is meant by your chain reaction. There's a great little graphic there. Chain reaction refers to the process in which neutrons released in fission produce an additional fission in at least one further nucleus. This nucleus in turn produces neutrons, and then the process repeats. Great little GIF. There it is. Ding, ding, ding. That's how it happens, right? And then this is why they can be so difficult to control, right? If you're not controlling this process, you've got like a runaway chain reaction, and that's not good. So to maintain a sustained or controlled nuclear reaction, every 2 or 3 neutrons released, for every 2 or 3 neutrons released, how many must strike other uranium nucleus? Yeah. Oh.
Particle accelerators.
Well, right now with particle accelerators, really what we're doing is we're accelerating particles, so positrons, into existing atoms to create a new element, right? That's what we're doing. We can't, at this point, we're not good enough at like consistently accelerating your two hydrogens into you want the low mass things because they're easier to combine than the high mass thing. High mass is easier to split, low mass is easier to combine, theoretically easier. So how many for every 2 to 3 neutrons that are released, how many must strike another uranium nucleus? How many do we want? Look at the graphic. How many? Liam, just one. We only want one. We got to keep it under control. So that's what we're aiming for. If we have other things going on, then you have an uncontrolled reaction, right? So if this ratio is less than 1, the reaction dies out. If it's greater than 1, you get an atomic explosion. It just is completely uncontrolled. Yeah. That is super complicated, and way above my pay grade. But that's what nuclear engineers are for. And that's why they've chosen uranium and plutonium. Apparently, those are the easiest to control. It has to do with a lot of conditions. It has to do with obviously the amount of material you're using, the temperature at which you're doing the reaction. It's a whole thing. You should look that up and see. I'm going to admit, I have no idea how they make those decisions. That's pretty advanced. So you asked earlier, like, what are some other uses for isotopes? Well, here we go. We have half-life. All right, so this is an interesting and useful aspect of radioactive decay is half-life. Yeah. So that is Voldemort. So we know how long it takes for a lot of these radioactive isotopes to decay and become another element. And because of that, we have a known value that we can apply to certain situations. So if you've read the Harry Potter books, you know that when they talk about Voldemort drinking the blood of the unicorn, they say, you have slain something so pure and defenseless to save yourself that you will have but a half-life, a cursed life. From the moment the blood touches your lips. Okay, well, this is the thing. I don't know if y'all remember, but a little while back, Starbucks put out the unicorn frappuccino. And it was like a thing. It was a limited time thing. Everybody went and got it. It was this yummy little drink. That's what it looked like. And all the memes came out at that time for the unicorn frappuccino with Voldemort. So it was fun. So the joke was, if you drink the frappuccino, you've got a half-life, right? So now we use this half-life for radiocarbon dating. So you can date a fossil by saying, okay, it's in this layer of rock, and this layer of rock is X number of years old. Therefore, I'm going to relatively date, relative dating. You're going to relatively date it to the same age as a layer of rock. Or you can say there are other fossils nearby and I know how old those are. So since this one's in the same layer, it's probably the same age roughly. But then you get things that happen where things get moved around or taken out of place, and you don't have any of those things for a relative to comparison. So radiocarbon dating gives you what kind of an estimate, do you think, as opposed to a relative? Better than rough. Exactly. So what we're looking for is objective. It's objective. You're not comparing it. It's not relative to anything else. And here's how it works. You've got carbon in life forms, right? Anything that was alive is organically based. That's what we're about to move into, is organic chemistry. So there's carbon in these life forms. There's carbon in you. There's carbon in your bones, whatever. There's carbon in dinosaurs, right? But radiocarbon dating only works but so far back. It can't take us way, way, way back. We use different elements for depending on how far back we're trying to track something, trace something, get a date for. But the way it works is, so you eat leaves, and like say you found a skeleton out in the woods behind your house, and you're like, how old is the skeleton, right? So you want to find out how old the skeleton is. You might take a bone sample, and then you're going to find carbon in there. Now, this human consumed either animals that consumed plants or the human consumed plants. So you've now got carbon in there, right? Well, carbon is in two forms. You've got your regular carbon, and then you've got like your carbon-14, which is carbon that's been, it's nitrogen that's been altered into carbon, which I'll show you in a minute. But you get carbon in two different forms. The carbon-14 is going to decay every 5,730 years. There will be half as much as what you started with. So you take your level of carbon, regular and carbon 14, and you compare them. And you can watch the 14 decrease by this exact amount, exactly half the many you started with by this number of years. So at 5,370 years, you're going to have half the carbon 14 that you started with. Then you have 11,460 years, you have a quarter of the carbon 14 you started with. And then you get 12.5% after 17,190 years. And we know that pretty exactly. So it's an objective way to date something. So this is going to show you kind of how you get to the carbon 14 in the first place. Y'all back there, seriously, it's exhausting.
It became my bridge to connect with people.
Okay.
My name.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
So that's one use of radioactivity is radiocarbon dating. And that one's probably one you're familiar with. You've probably heard it before, seen it before, come across it before, right? But then we have other practical applications, and some of these you probably have not even thought of. So Americum-241, oop, do not mean to click that button. Go away. So look at all of these. These are all different uses for different isotopes. Let's go away. There you go. So for example, californium is used to inspect airline luggage for hidden explosives. Okay. We just talked about carbon-14. Cobalt is used to diagnose as a tracer to diagnose pernicious anemia. So tracers are when it's a radioactive element that you're following through a process. You can see how the process works. Gallium is used in medical diagnosis. Iodine is used to treat thyroid disorders. Yeah, all kinds of stuff. Krypton is used in indicator lights and appliances such as clothes washers, dryers, stereos, coffee makers, and to gauge the thickness of thin plastics and sheet metal. There's all sorts of applications for these things. Here are more. Nickel, phosphorus, here's plutonium. We talked about how uranium and plutonium are typically used as power sources. Plutonium has powered more than 20 NASA spacecraft since 1972. That's craft, not missions, right? Radium makes lightning rods more effective. Now, strontium. I want you to remember these strontium ones, okay? Because we're going to be talking about strontium in just a minute. Strontium-85 is used to study bone formation and metabolism. And strontium 90 is used in survey meters by schools, military, and emergency management authorities, also cigarette manufacturing sensor. What? Look at all these.
Strontium 85 and 90 are radioactive, but not like strontium 87 or 89.
Sometimes there aren't the ones in between, they just don't exist. They're too unstable.
Or maybe
They don't, they're not a thing.
Or maybe
Yeah.
they're used for the.
Yeah, well, usually it's because they're not a thing. Yeah. And it all has to do with what forms it in the first place. It's a whole, you could do an entire year worth of study on just this stuff, you know, and we're doing like one lesson of whipping through it. Like you can, it's very involved. But there's your uranium. Look at this one. Uranium-235 is used in power plants, but uranium-234 is used in dental fixtures like crowns on your teeth. Right? So we have all kinds of uses for these different isotopes. We've learned what to use and how to use it, and we're doing pretty well, I would say. Here's your strontium. Now, I don't know if you know this, but isotopic testing can be used to tell where you've been. Strontium knows where you've been. It knows exactly where you've been, or roughly a good range of where you've been. So pay attention to this because this applies to the long video at the end of class. Okay.
I told you, there's a simple way for me to figure out every place you've lived for the first, say, 20 years of your life. Because there is one. All you need to do is let me borrow a couple of teeth so I could measure how much of the element strontium is in them. If we actually tried this, the tooth extraction part probably wouldn't be too much fun for you. And there's also plenty of easier ways to get the same information, like by checking social media or just asking. However, the technique is super helpful for anthropologists who study ancient humans, because it's not like skeletons can just tell us what their lives were like. And knowing where a person lived can tell you a lot about them. For example, if someone grew up far away from where he died, that might mean he was part of an invading army or an immigrant seeking a better life. By the same token, if a person lived a long life and was buried in the same place where she was born, it might be logical to guess that she had a pretty cushy life, didn't need to move to find food or flee from enemies. Your teeth hold a lot of information about your life story, and scientists are learning how to read it thanks to the properties of strontium. For one thing, there's more than one isotope or form of strontium. For anthropologists, the most useful are strontium-87 and strontium-86. They're the same element, but 86 has one less neutron. Another thing that's cool about it is that most strontium doesn't start out as strontium. Instead, it's one of the products that forms when another element, rubidium, decays. So the place where you live has its own ratio of strontium-87 to strontium-86 based on what your local geology is like. For example, older rocks have had more time to decay, so they will have more strontium-87. Rocks that have lots of clay or granite in them also tend to be high in rubidium, so they have more of the 87 isotope too.
That's
and
here.
whether you like it or not, all of this stuff in your local soil and rock ends up in your diet. It filters into the water and the plants and then travels up the food chain until it gets into your mouth. And then the strontium you eat and drink gets incorporated into your teeth. The enamel coating your teeth contains a lot of calcium, and strontium is like calcium in a lot of ways. It reacts with a lot of the same compounds, and it's a similar size. So when your body is making new teeth throughout your childhood, sometimes it'll incorporate strontium instead of calcium. And the strontium isotopes will show up in the same ratios that they had in the water you drank. Anthropologists can measure those ratios in your teeth and use that info to learn where on the planet you were living when those tissues formed. For example, the strontium in the molars you got when you were around 6 will tell anthropologists where you lived for the first 6 or so years of your life. And the ratio of isotopes in your wisdom teeth will reflect where you lived around the age of 9 when they started forming until your body was done making the enamel, which can be as late as your 20s. And once a tooth is formed, it's done. It's not getting any more new calcium, so the strontium ratio is set forever. So, if anthropologists find a tooth from a skeleton, they can figure out where the person was born and where they grew up, even if those were different places. This is especially handy if the placement of the skeleton seems weird. Consider this case study. A mass grave in the ancient settlement of Cahokia, near modern-day St. Louis. The grave contains the remains of 39 people who were buried about 1,000 years ago, many showing signs of some kind of violence, like stone points in their bones. For a long time, researchers thought these people were from outside of Cahokia and were killed as war captives or intruders. But recently, they tested the strontium in the victims' teeth, and it turned out that most of them were actually from Cahokia, born and raised in the same town where they were killed. This has made some anthropologists rethink their theories about the nature of life and death in America 1,000 years ago. Just one of the discoveries made possible by studying a little element in human teeth. Strontium, man. It knows where you've been. Thanks for watching this episode of SciShow, brought to you by our patrons on Patreon. If you want to help support the show, just go to patreon.com/
So that's kind of fascinating, right? Did you know that? Did anybody know that before you watched that? That you can check your strontium in your teeth and know where you've lived? Yeah.
Wisdom teeth.
Yeah.
I think it's-
Yep,
so in 1,000 years, will some scientists just not know?
they won't know where you lived.
9 to 20?
Yeah, they may not know that. Yeah, they may not know some of that. They use isotopes in other ways too to test where you lived, but strontium in particular is one. And they can also test isotopes in other parts of your body, not just your teeth, but other parts of your body to tell where you lived more recently. But your teeth can definitely tell where you grew up, but they can tell where you've lived more recently, which is going to come into play in a minute when we get to, it's like a case study that we're going to do. So what is the energy emitted when a nucleus forms? What did we call it? Asher? Nuclear binding energy. Yep. Okay. And what's a nucleon? Colin? Okay. Proton or neutron. What is the high energy electromagnetic radiation produced by decaying nuclei? What do we call that? Easier than you think. Colin.
The beta particles?
Yeah. It's gamma radiation. Yeah, radiation. So what is the high energy electromagnetic radiation? Oh, I just read that. Sorry. What nuclear reaction happens when two small nuclei combine? Lucas. That is nuclear fusion, right? Explain the difference between fission and fusion, Xander.
Yeah, I could say. And fission is where two nuclei separate.
Right, large nuclei break apart in fission, small nuclei fuse together in fusion. Very good. So name the process that describes an unstable nucleus that emits particles and energy. James. Radioactivity, which is nuclear decay. Yep, okay. 7, define critical mass. Who knows this one? This in your notes? Anybody? Jordan?
It's it's the minimum amount of mass or the minimum amount of neutrons required to start a chain.
Yes, it's the critical mass is the smallest mass of radioactive material needed to sustain a chain reaction. All right, what's half-life? Caitlin.
It's the amount of carbon-14
That's one example. The amount of time, Andrew? Right, it doesn't have to be carbon-14, but yes, it's the amount of time required for half of the radioactive isotope to decay. So half of what you started with has decayed is the half-life, and then that keeps getting halved, right? And what is the combination of neutrons and protons in a nucleus known as? You know that one? They wanted nuclide here. That's what you call them when they're all together. And name 2 types of nuclear changes. So this would be fission or fusion, you could say, for example. Those are changes. All right. So, and now here's our fun. This is going to be different than what we usually do. We don't usually watch long videos, but this was worth it. So this is a real contemporary case that involved isotopes to help identify some Jane Doe victims. 4 Jane Doe victims that were found together. And here's the crazy thing. Of the 4, that was one of the first things they started with. They did a bunch of stuff. This was one of the tests they used, was the isotopic testing in teeth. Of the 4, they have identified 3. There is 1 remaining Jane Doe that has not been identified. But here's the crazy thing. They know who her father is. They don't know who her mother is, and they don't know who she is. They can't find a record of her. But they did use some radioactive isotope testing as part of this process. They got DNA involved in the end, but they started with the radioactive isotopes. So this is known as the Bear Brook case. And this is a great case study example to show how you can apply multiple things, multiple different testing procedures to a sample and try and get different information that will help you piece together a very complex puzzle. So in the end, it was DNA that positively identified 3 out of 4 of the victims, as well as the perpetrator. But the 4th victim, they call the middle child, and she is still unidentified. So this is an adult woman, 3 minor children. Those are your 4 Jane Doe victims. The middle child, not the oldest or the youngest, is the one that is still not identified, still today. So isotopic testing showed that the woman and the children lived together in the northeastern United States for between 2 weeks and 3 months before their deaths, likely near where they were found. So that's not strontium in teeth. That's another type of isotopic testing, because strontium in teeth would show years back for at least the woman. The child, you could probably use some of that information for the children because their teeth are still forming. Some of these children are actually, they're all very young. They're all very young. Isotopic testing showed that the middle child, the one who's still unidentified, probably spent most of her childhood in either the upper Northeast or upper Midwest, perhaps Wisconsin, but we're not sure. So this is a longer documentary. If in the end you need to split, you can split, but I want you to know there is a podcast for this, which is outstanding. It's called Bear Brook. That's the QR. I've also put it in your resources. So if you like listening to podcasts, this is a great one to listen to. So the case is also a perfect bridge into the biological chemistry that we're about to study. So hopefully it'll get you interested in the type of forensic DNA that we're going to be discussing next year in biology. So this is the middle child. Actually, what I'm going to do is I'm going to come out of here. There's nobody absent, right? So I'm going to go straight into YouTube so we don't get any of that weird. I'm going to end the. Who's on? Liam's here. I'm going to stop the share so we don't share this whole video because I'm including the thing.